So we just talked about the classical description of polarization. It has a pretty nice mathematical description, but we saw how that mathematical description results in a non-physical result, which is that a single photon can have multiple phases, right? The X and the Y component of the electromagnetic wave can have different phases, and that just doesn't make a whole lot of physical sense, because we know that a single wave has a single phase, right? Um, and if you try to think about how electromagnetic waves actually exist in space, the idea that they might have just an X and a Y component also doesn't make a whole lot of sense. So what the modern description of polarization is that every photon has angular momentum. And with angular momentum, that means that it has some spin, right? And we can describe that spin as either being left-handed or right-handed. So if you take either of your hands and put the thumb in the direction that the photon is going, and then look at the way your fingers are wrapped around the photon's vector that's going in the direction it's going, and whichever one describes the direction that the photon is spinning, that's the spin that you have. So you can either have left-handed or right-handed spin. And the so physicists have measured this, right? They know that the angular momentum that a photon can have is quantized. Man, that's a word I cannot say. I struggled in the last video. It's either plus or minus Planck's constant times its frequency, right? So this is the amount of angular momentum that each photon has, and it's it can either be plus or minus, right? Where plus is the direction it's traveling, and minus is going backwards. So again, that's the difference between right and left-handed spin. So linearly polarized light is when a photon has equal probability of traveling with either right or left-handed spin, right? So remember how we talked about how photons can go through both slits at the same time with a double slit experiment. This is something similar where a photon could exist at the same time with either right or left-handed spin. And in that case, we have like vertically, linearly polarized light. And as we change the probabilities of whether or not it is right or left-handed polarization, we can get elliptically polarized light, decreasingly elliptically polarized light, all the way to circularly polarized light in this direction. Or if we go in the other way, you know, elliptically polarized light to circularly polarized light. And all this does is change probabilities, right? Where we have 50-50 in the middle. And then if this, now the real difficulty is like, well, we have vertically polarized light. What does horizontally polarized light look like? Well, that's just changing the phase lag between the right and left-handed polarization probabilities, right? So it's either going to have a 50% chance, if it's horizontal, it's going to have a certain phase lag between its right and left-handed spin, and if it's vertical, it has a different phase lag. So you still end up with the same number of quantities to describe, right? We have now, instead of an angle. So before we had an angle and we had a phase lag, right? We had an epsilon. Now we have a probability and a phase lag. Okay, so mathematically, not any simpler really, but more physically realistic. Now the real problem is if you go online and do a deep dive and try to get a good explanation of what this circular polarization means and how it works with, particularly how it works with your sunglasses, right? Or we're going to talk about reflection and polarization. there's no good explanation. Like people are just like, well, spin interacts with the thing, and the reason they have no good explanation is nobody really knows what photon spin is physically. They know it has it, right? They know that electrons have an angular momentum. They know that photons have they know everything has an angular momentum. You have a net angular momentum according to quantum mechanics, right? Even if you're not spinning, all the all the all the particles within you summed up results in a net angular momentum. But what exactly this angular momentum is not clear, right? And nowhere is it more obvious that this angular momentum is not clear than in polarization, because in our next video we're going to talk about how to polarize light, and you'll see that, for example, in your sunglasses, the classical explanation of polarization makes complete sense. In fact, with all of the explanations of polarization, the classical method makes complete sense, which is why it's so popular, right? And the modern explanation really breaks down in terms of have given you a way of like physically understanding what's going on. So yeah, okay, so that's the modern explanation of polarization. We're not going to mathematically go into it, and in our next video we're going to start going into some methods of creating polarized light.